When you think about what makes something strong, your mind probably jumps to perfection, right? You imagine the strongest stuff must be flawless, perfectly put together, right down to the last atom. But what if I told you that's completely wrong? What if, in the world of materials, real, usable strength actually comes from imperfection? Okay, let's get into it.
So let's just tackle that head on. Is a perfect crystal, this ideal arrangement of atoms, really the best, the strongest? Is it really perfect? The answer might surprise you. It's a huge, emphatic no.
I mean, just look at this. This is the theoretical ideal, a perfect crystal lattice. Every single atom is exactly where it's supposed to be, locked into this beautiful repeating pattern. And you'd think, wow, that looks invincible. To break that, you'd have to snap every single one of those atomic bonds along a plane, all at the exact same time. That should take a colossal amount of force. But here's where we run into a major paradox. That incredible strength that theory predicts for these perfect crystals, we just don't see it in the real world, not even close. There is a massive gaping chasm between what the math says should happen and what we can actually measure in a lab. And listen, we're not talking about a small difference here. This isn't like being off by 10 or 20%. We are talking several orders of magnitude. That means the real strength is 100, 1,000, sometimes even tens of thousands of times lower than the theoretical strength. To put that into perspective, the strength of a perfect crystal should be measured in gigapascals. That's billions of pascals. But the materials we actually use every day, the steel in our buildings, the aluminum in our phones, their strength is measured in megapascals. That's millions of pascals. They are just profoundly weaker than they should be. So you gotta ask, why? What is going on here? What's the secret ingredient or the missing piece that explains this enormous gap between the ideal world of theory and the real world we live in? Well, the answer is just fantastic. It's the power of imperfection. It turns out those so-called flaws in a crystal aren't weaknesses at all. They're the very reason materials have useful properties, like being able to bend instead of just shattering into a million pieces. And the unlikely hero of the story is a specific kind of flaw called a dislocation. So what in the world is a dislocation? Well, think of it as a line defect. It's like an extra half row of atoms got shoved into the crystal structure where it doesn't quite fit. And here is the absolute key. The movement of this single line of atoms is what lets a material permanently change its shape, what we call plastic deformation, without just snapping. Okay, here's the best way to think about it. Trying to break all those atomic bonds at once, like in a perfect crystal, that's like trying to move a giant heavy rug by grabbing one end and pulling the whole thing. It's going to take a ridiculous amount of effort. But moving a dislocation, that's like putting a little wrinkle in the rug and just easily pushing that wrinkle all the way to the other side. It takes way less energy. So let's see this wrinkle in action at the atomic scale. When you apply some force, that extra half plane of atoms, the dislocation, doesn't just sit there. It starts to glide along a very specific path inside the crystal, kind of like an atomic highway called a slip plane. And there it goes. You can see the dislocation just zipping through the crystal. It's not breaking everything at once. It's just breaking and reforming one single line of atomic bonds at a time as it moves. It's this incredibly efficient, low-energy shortcut instead of that brute force approach. Finally, when the dislocation hits the edge of the crystal, it pops out, leaving behind this tiny, permanent step. Now imagine billions and billions of these things happening all at once. That's exactly what's going on when you bend a paperclip. It's not breaking, it's just trillions of these tiny flaws moving around. Okay, so if these flaws are actually the source of useful properties, it opens up a really cool idea. What if we could control them? What if we could move beyond random flaws and start creating defects by design? Well, that's the whole idea behind a field called defect engineering. And it turns out engineers have a whole zoo of defects to play with. You've got your zero-dimensional point defects, like one missing atom. You have the one-dimensional dislocations we've been talking about. There are two-dimensional planar defects, like grain boundaries, which are the seams between different crystal regions. And you can even have three-dimensional defects, like tiny clumps of another material sprinkled in on purpose. So how do they do it? They've got this amazing toolbox of techniques. They can just physically beat up the material, rolling it, compressing it to create dislocations. They can use chemistry, alloying it with other elements. They can use really precise heating and cooling cycles. They can even get high-tech and bombard it with ions, or use 3D printing to build the defects right in from the start. But here is the most important insight of all. This is the whole point. The goal is not just to add random defects and make the material messy. No. The goal is to organize these defects into very specific, highly controlled structures that create incredible, sometimes brand new properties. And this is where we get to the payoff, because when you truly master the art of imperfection, you start to get results that honestly look like engineering miracles. Get this. Take piezoelectric materials, the stuff in speakers and sensors that creates voltage when you squish it. By creating these carefully organized networks of dislocations in a material, scientists boosted its performance by a factor of 19. Not 19% better, 19 times better. Or how about this one? Phase change materials, the kind we use for things like rewritable data storage. By using defects to control how the material flips between states, engineers made it 100 times more efficient. These aren't just tiny improvements. These are total game changers. And the list just keeps going. This is the secret behind making steels that are somehow both stronger and less brittle at the same time. It's how we're making materials that can turn waste heat into electricity more efficiently than ever before. It's how we build things that can survive the radiation of deep space, and it's even pushing the limits of things like superconductivity. So if you walk away with just one thing from all this, let it be this. It is not the mere presence of defects that matters. It's their organization. Random flaws? Yeah, those can be a weakness. But organized, engineered flaws? That's revolutionary. And this picture just says it all. You're looking at the grain boundaries inside a piece of metal. To you and me, it's just a solid chunk of steel. But through a microscope, you see this absolutely beautiful, complex mosaic. These are the flaws. These are the organized imperfections that actually give the material its strength, the very things that hold our modern world together. It really is a powerful way to look at things. The very thing we thought was a weakness was actually the source of strength the whole time. Which kind of leaves you with one last question to chew on. If the hunt for perfection leads to things that are brittle and fragile, and controlled imperfection is the real secret to strength and resilience, what else out there are we getting completely wrong?